problems I have.
Hi, I'm Darius, and by the way, I'm hard of hearing, so I've been using this fancy AI thing to transcribe this, but it's not going to remember it. I couldn't point it out. Anyway, I'm a programmer, and I used to work at the JPLAI group, but I've not actually used any really deep format and stuff, and I've really just been more in programming languages. I did write an article on binary decision diagrams. Got that up on the web, running thing that implements it so you can learn all the details and push it away. Just to ask me about that, if you're interested in that. Also, one more thing relative to this meetup, I made up this little puzzle game that is directly modeled on the satisfaction problem. So you have variables and you have classes, and that's how it is there. So it's up on the web now.
Oh, okay. My name's Dan. I'm a researcher at the University in Denmark, and I do like programming languages, distributed systems type of stuff. What else should we split? I think that's it.
I mentioned the podcast last time, so I think
yeah.
it's probably worth
if like you have like an otherworldly feeling seeing my face while and listening to my voices, because I'm in a mildly famous podcast called Tech Theory for All. My friend Pedro hosts that one, and I'm sometimes on there. But yeah.
Occasionally venture into areas like that absolutely overlap with our stuff, like the when they had SEL4 stuff, a little bit of with German Klein and everything, so that's cool.
Yeah, yeah. So I'm really excited to see how it goes. I'm sad that I missed the last one. I missed a whole bunch of
Glad to hear.
Yeah, thanks for putting this together. It's really cool.
Thanks.
We'll do zigzag.
Oh, hey, I'm Nate. I'm a student at Texas State in mathematics, and I am also a software engineer with Charlie here in Cass. And I'm working on Texas State's Space Lab team, and we're putting up a satellite early next year. So we're working on that, and yeah, I'm very excited.
I'm Pantaleano, and I am a software engineer with Nate and Charlie, and I like complicated math puzzles. It's not hard.
Hey, I'm Sahil, Linux kernel dev, and broadly interested in theory and competitors.
Howdy, my name is Misha, and I'm a hardware design digital audit guy, so kind of in it for selfish purposes, trying to maybe work out a project of formally verifying a 3-bit error correction scheme, essentially, for PCH. Because otherwise we're just throwing bits at it and then making sure that it's good enough as the current standards at our company. So maybe moving that forward a little bit. So
I'm Vincent, really interested in like math, computer science, all that kind of thing.
Hello, my name is Constantine. I'm a software engineer, and I have a master's of mathematics and computer science degree. And I'm interested in test-driven development, so I want to learn about full method.
My name is Chris. It's my first time here. I'm a software engineer, and I cross the hall and see the group. And I would like to meet engineers and programmers. I'm a company founder. I have a company. It's a software company. We provide other services, and being a part of this kind of group for more than 4 months, and be glad to be here seeing like a code.
I'm Andy. Most recently I was VP of a Bluetooth Low Energy startup, but now I'm semi-retired. But in the previous life, I was a VLSI designer. So my context for dealing with formal methods is BDD and verification of things like Verilog versus schematic versus layout. So that's kind of where my lens through which I view this kind of formal method stuff.
I'm Robert Stroff. I've been a software engineer, programmer, developer, and various subject roles for a bit, kind of all over the place, from web stuff to embedded devices and to GPS and a lot of longitude, latitude calculations and so on. I was aware of formal methods all the way back in college and always dismissed it as being like too ivory tower to be worth it. And I have a general feeling that that's not true anymore, and I want to learn some of the more practical sides about it. How you know what size and types of problems and code that's like reasonable to approach this in a human time frame.
Cool. Well, thanks everybody. Thanks for coming out, and we'll go ahead and get started. First up, we want to get a thank you to our sponsors. So Capital Factory is being gracious enough to allow us to use this space every month on the fourth Wednesday of the month. We're going to have to figure out what that means for December and November. But apart from that, we do have the space reserved, and so we are welcome to come here and meet every time. Thanks. And then, in addition, we now have a Zulip. So, if folks are interested, we have got, it's kind of like another chat system. I know, yet another chat system, but it seems to be a bit more popular in some of the academic circles. And so as I was explaining to some folks a couple days ago, the Isabel interactive proof assistant is using, that community is using Zulip. That's a pretty active one. There's also a community for Krusty, which is one of the major efforts to formalize Rust. There's also being used for, there's a variety of different ones, and it seems to be particularly popular with these really deep technical communities that are distributed globally, which doesn't entirely describe us given the global aspect of this, but apart from that, I think there is a bit of overlap with where our area is interested in this particular setup. So if you're interested in getting on there, let me know. We've got it so that it's like invite only setups right now. But if you give us, let me know, we'll get you invited in there. There has been spam in some of the other communities, and so that's why it's like, at least for now, let's keep it invite only and figure out how we want to proceed. So but we do have, they've sponsored us, have given us a free upgraded plan, so we are no longer bumping our heads immediately against the size issues. And just as a reminder, what do we mean when we say formal methods? Okay. And so in this case, this definition we came up with last time is formal methods are techniques and tools which use rigorous mathematical logic to design, analyze, and verify systems with provable properties. And those provable properties might be things like correctness, reliability, or security. Or as we will see today, you might get things like satisfiability, or falsifiability, or equisatisfiability, all kinds of things like that. So, this talk is not as filled in as I was hoping it would be. I very quickly discovered that, it was like my goal is to get all that I know about stat solvers into one spot. It turns out I knew a little more about it than I thought I did. And also, in trying to even do that ridiculous thing, I found out there's a lot of things I thought I knew I was wrong about for stat solvers. So there's a bit of a journey we're going to go through, but at least to give you a high-level idea of what we're even talking about. We're going to start with this example about conditional simplification. I was hoping to get nice looking code to show you for this. LaTeX is being a piece of crap, so I couldn't get the code quite working, but I think you will be able to imagine what I'm referring to when I say something like a conditional statement. So a conditional statement is like an if, and then you have a then, and then some code gets run, maybe there's an else, maybe there's an else if. So let's give some names to the individual parts here. So the whole thing, like your old block where you start with an if, you end, maybe you've got a then, maybe you've got a fi at the end, whatever it's going to be, the whole thing, we're just going to call that a conditional statement. It's largely the same, regardless of what programming language you're talking about. This concept is very common, so we're just going to call the whole thing a conditional statement. So the thing inside of the test, so in your if whatever, we're going to call that a guard. So that's usually the terminology that computer scientists would use when referring to that piece. For a conditional statement, it is a guard that is, in a sense, it's protecting execution from entering that section of code. Okay? I think as programmers, this is a concept we're probably all familiar with, but we just got to make sure that we're using the same terminology here. That's the guard. Okay. Inside of there, we've got the code block. It's kind of what you would expect, and then we have. Sometimes they will explicitly call it an alternate code block. That's the thing that comes after the else. It doesn't come up as often that people would like call it out as something special, but if they do, that's the terminology they use. So sometimes when we're working on code, you might see something like an if false, and so if you're looking through a piece of code and you see someone wrote if false and then did a bunch of code, well, that means that code's just, it's dead code. It's never going to ever run. They just did that as a way of maybe keeping something there to keep their spot, make sure they didn't lose something that they were starting to work on or something that's only being used for testing or whatever. That is essentially what's going on. Whether or not that is a good idea is another topic that can be discussed later. That's what is happening at the very least. And when we're talking about our guards for today, I know this is a longer thing, but you're just gonna have to bear with me on this. We're gonna ignore side effects happening inside the guard. So in a programming language like C, you'll see all of the time, people will do something like a, fget C inside of a loop to do an iterative character consuming process. If you're doing something that is character based, you're trying to read a byte at a time, you might do something like an fget C as a side effect inside of your guard. It's a really common pattern for C. Some programming languages hate it, but it simplifies our conversation for today if we just pretend like that's not happening. They're not magical function calls, these are just variables. That's it. We're just talking about Boolean variables. And we're not even talking about math here. We're not even talking like A is greater than B or something like that. We're talking about A and B, A or B, things of this nature, for the most part today. So sometimes when we go and look at this, we can tell right up front, like we said, if you have like an if false, well, okay, we don't have to go and check on anything. If it's literally if false, there's no magic going on. You know that you can just skip the entire code block. Or if it's an if true, another strange thing, you'd be like, why is that even there if it's if true? Like then we're always executing the code block. Again, these are things the compiler can figure out against it. It might complain about it, but as far as the code is concerned, it's not something that's necessarily wrong, even if it's maybe not desirable in some sense. But the compiler can figure out a sensible thing to do if it sees an if false or an if true, literal. Where it gets a little more interesting is what if there's some other reason? Something about the nature of the question, the way that we phrase the guard, that we know it couldn't ever be true. Maybe it's not literally if false, but it's something else that we know can't happen. I don't just mean like, well, if we ran out of hard drive space, and well, we agreed we're not gonna run out of no. I mean like something we could know a priori can't be happening, just from the logic itself.
Unsigned if less than 0.
Yeah. You know, or
X and not X.
exactly. That's a great one. X and not X.
Sorry to do a minor tangent. There's like a trick complete game where you build up a computer from the circuits, and in this code, there's the concept of a conditional jump. And so you want to do an unconditional jump. You have to make the condition guaranteed to be true. You can be creative with that, you know. If register 1 equals register 1.
Exactly.
Constant 0
Exactly.
equals constant 0.
So what if you have something that can't be true? Or here's another one, a similar setup. So for that one, we would call it dead code because for whatever reason the guard couldn't possibly be true. We know that the thing inside of there is dead code. Same thing with the opposite. If the code, something about the way we've structured it, it's always true. Well then okay, that code's always gonna run. It's like the opposite of dead code, live code, but that's not that's not really the term we would use, but yeah. It will always run. Generally speaking, we would just call that control flow simplification. We're just removing the if from there. But then there's other times where you can't eliminate the path, and you still have to execute it, but you still have to also do the check because the check could actually change based on conditions at runtime, or at least when the program starts, some flag or something that got passed in. And so sometimes you actually just have to include the whole thing as a compiler or whatever. So how do we deal with that? Well, let's give the kind of high level overview of the terminology we're even talking about, how we can approach something like this. So right up front, Boolean formulas. The stuff that we're talking about, these guards that we were saying. Again, we're saying ignore the possibility of side effects for now. We're going to ignore the possibility of any kind of arithmetic, any kind of math or whatever. It's just ands and ors and nots. That's it. If you're talking about something that's just variables with fixed values, ands and ors and nots, that's it. And the variables can only be true and false. Now we're talking about something we would call a Boolean formula. And so that is, if we're talking about the simplest kinds of things you might put in a guard of a conditional, it's going to be a Boolean formula. Okay? It's worth pointing out, we're just talking about ands and ors and nots here. You could have Boolean formulas that involve things like XOR, NAND, implies, other things like that. If you're just talking about Boolean variables and operations that don't change them from being Boolean, you can do whatever you want. But generally speaking, we kind of reframe all of the other ones when talking about them in a formal sense. We talk about them as a mathematical idea, and we're trying to analyze what's possible to do with these things. We just smash them all into ands and ors and nots because you can represent anything you can think of just with those.
Right. And or not.
The and or not?
Right.
Yeah. Okay. This term's annoying for the programmers, but you just gotta accept it. Unfortunately. Assignment, which, as a working programmer, you might think, well, I know what that is. That's when I have a variable name and I want to put something in it. And that's not entirely different from what a computer scientist would mean when they said assignment, except the difference is they mean all of the assignments that are happening in the entire state at the same time. So in a sense, from the perspective of a working programmer, when a computer scientist says the word assignment, think of the state of memory. That's what they mean. All of the relevant parts of memory. Because it's going to come up, because if you look up anything to do with SAT solvers, you're going to see them talking about assignments that produce truth, or assignments that produce falsehood, or witnesses, which are a specific assignment that produces one of these values or something like that.
From my perspective, I call it like a solution candidate.
Yes, a solution candidate, exactly. It's assignment is kind of a strange term to be perspective of a working programmer, but from a computer scientist, it just means what are all of the values at once. So, for example, if you had variables A, B, and C, again, we're talking about Boolean variables here, which just happens to be what we're talking about at the moment. An assignment would just be, that A, B, and C are all false, or maybe A, B, and C are all true, or maybe A, B, and A and C are true, and B is false, or any possible combination of specific values you might have at a particular point in time. That is an assignment. And I'm harping on this because if you ever look at any of the terminology about stat solvers, they're going to throw around the word assignment like it's candy. And you're going to be like, what the hell are they talking about?
So an assignment is a singular choice out of the possibilities.
Yeah, a singular choice of the current state of all of the variables. That's what it means. It means one state, in a sense. Okay? So, now we're getting to the meat of it. Satisfiable. So we were talking about Boolean formulas. Remember, those things which are just variables, which are true or false. That's all they are. And you're just using ands, ors, and nots. That's it. That's all you're using. Ands, ors, and nots. You've got parentheses to show what order these things are happening in, but ands, ors, and nots, Boolean variables. A Boolean formula is satisfiable if there exists any assignment, so remember, just some state, of the Boolean values to those variables, whatever variables are in that formula. If it's possible to find one of those assignments that makes the entire Boolean formula true. Okay? Well, there's a lot of different Boolean formulas we can talk about. It's almost more interesting to look at ones that can't happen. And so here's some of the examples we talked about. True and false, these are counter examples. These are Boolean statements. Each one of these are Boolean formulas. These are ones that aren't satisfiable. And I'm calling this out because most Boolean formulas are satisfiable. But these aren't. Okay? So true and false, that is not satisfiable. A and not A is not satisfiable. There's no value you could come up with to give A that would make A and not A be true. Same thing for A and A implies B and not B. And we said, okay, A implies B. Okay, so if we know A is true, then we know B is true. We've just said that A is true. And we just said that not B. So this whole thing, there is no value for A or B that could ever make that statement true. And same thing down here. In a sense, this is kind of like saying A not if and only if B. This is like A implies not A if and only if not B, and A if and only if B. So in a sense, it's just like saying B and not B at the same time. So it's not. These are examples of Boolean formulas that could never be satisfiable, which is the weird exception, because normally they are satisfiable. Here's the opposite, falsifiable. A Boolean formula is falsifiable if there exists some assignment that makes the whole statement false. Again, most Boolean formulas are falsifiable, just like most Boolean formulas are satisfiable. But here are some examples of ones that aren't. So in a sense, all of these are falsifiable. In fact, they're only falsifiable. All of these are not falsifiable. In fact, they're all satisfiable. They're only satisfiable. So true or false. That's always true. A or not A. It doesn't matter what value you give to A, that is always true.
Am I right that in some contexts they refer to unfalsifiable formulas as tautology?
Yeah, tautology, exactly. So a lot of times a Boolean formula that is satisfiable, well, we'll get to what happens with it, but if it's not satisfiable, that would be a contradiction. If it's not falsifiable, that would be a tautology. And so these are all tautologies here because they're not falsifiable. Again, I could give you lots and lots of examples of statements which are falsifiable, but you're not even going to get a sense of what that means because there are so many of them that it's the vast majority of Boolean formulas are falsifiable. It's remarkable that these are not. So not A implies A, that's another one that's like, well, it doesn't matter what the value of A is, that's going to be true. And same thing with A implies, you know, if and only if itself. A could be true or false, that would still be true. And so then you get something like contingent, which is the vast majority of Boolean formulas out there, which is a Boolean formula is contingent if it's both satisfiable and falsifiable. So that means these are the normal ones, where it depends on what the values were. So just a variable, a Boolean variable that could be true or false. All right, well that means that the Boolean formula that's just A, that could be true or false. The same thing with like A and B. Well, A could be true or false, and B could be true or false. So that means that A and B, you know, you could pull out a truth table or something, you would see that there are rows which are true, and there are rows which are false. That means it's contingent, because it has both kinds of rows. Same thing with A or B, same thing with A implies B. This one's similar to that previous one, where we said A implies B and not B. When we get rid of that not B, that changes it. Now it's contingent. So there are values for A and B which would make this true, but there are also values for A and B that would make this false. So going back to our original description about conditional simplification, if you got your if block and you're trying to have your compiler decide, do I include this code? What you're trying to check for, if that code is satisfiable, then that means that, you know, the code block is going to end up in there. If the code is falsifiable, then
then we need to check.
Yeah, then you need to. But if it's both satisfiable and falsifiable, you have the code block in there and you're checking it.
Yeah.
So, yeah. So, as we mentioned, there's satisfiability or falsifiability, and it turns out that every Boolean formula is either satisfiable or falsifiable or both. You're not going to ever have a Boolean formula that isn't either. It turns out this one's, I feel, is a pretty straightforward proof. So if anybody is curious afterwards, we can chat about why we can know this for sure. But every formula has to be satisfiable or falsifiable or both. You can't have a formula that is neither satisfiable or falsifiable. So now we're going to get into,
That is deterministic though, right?
So again, we're talking about like
The
Boolean
purely
formulas.
Boolean functions that are
Yeah,
deterministic.
Boolean formulas. Yeah.
Yeah.
Once you start to get into other questions
Yeah.
about like, well, what happens if the values aren't fixed? It's like, okay, well that's an interesting question, but it's no longer. It's a different problem. You may have to toggle one of the buttons on there. Yeah, there. Yeah, the light's not on, it's not powered. There. So, in addition to, you know, satisfiable, falsifiable, contingent, another piece of terminology we need to look at is equality, maybe, of some kind. This feels like the thing that maybe we're talking about. We'll get to that, whether that's really what we're talking about. But so, okay, you can probably accept that if you've ever done much like distributed logic stuff, you can see this A or not B and C is the same thing as this A or not B and A or C. Kind of distributing the or across that and there. You're distributing these disjunctions through the conjunction. So those two statements are definitely the same thing. They mean the same thing. They are equal in some sense. But it's also worth pointing out in the realm of computer science and stuff, a lot of times we don't really care what the variable names are. And what's interesting, when we're talking about things like SAT, sometimes we don't even care whether a particular variable is true or false. it needs to can be consistent whatever it's going to be, but we don't care if you pick the variable that's true, or you're like, well, I've decided I'm gonna have a different version of that variable that's always the opposite of what it's supposed to be. It's like, okay? And so as a result, most people working in SAT solvers would consider these two equations, these two formulas, to also be the same as those up there. And this first one, what we did was we just changed the names of the variables. Like A is now P, and B is now Q, and C is now R. It's the same thing. We didn't change anything about it. We just changed the variable names. And down here, this one's interesting as well. We changed the variable names, but we also decided that this new variable J just means the opposite of whatever B is.
We just change the sign convention.
We just changed the sign on it. Doesn't matter. From the perspective of something like SAT solvers, it doesn't really matter that much. You gotta be careful about doing that, but when you're talking to computer scientists, they'll know the difference, and so that I will point that out in case you're reading a paper and you're like, what just happened? That could have been what just happened.
Another context I would see that referred to as being isomorphic.
Yeah, in a sense, yeah, the isomorphic, yeah, there's a lot of different, depending on which branch of math we're looking
And
at.
as long as you negate all occurrences.
All occurrences, yes.
Don't get-
And to kind of get at some of the stuff, if we get over to, at some point, I think we might have a talk on the Curry-Howard correspondence. If we do, then it's going to be really important that we say, like, whether or not this variable can be replaced or not under a specific circumstance, because like it depends, is it bound on the outside, is it free? These are questions that are very important to be aware of, but from the perspective of what we're dealing with tonight, it can be a little bit on the flexible side. So with all of that, that means equivalence. So that means two formulas actually say the same thing. And so normally when we think about two things being the same, that's what we mean. That's what we're thinking anyways. But that's not necessarily what we're going to be talking about with SAT solvers. What we're going to be talking about with SAT solvers is this different thing called equisatisfiability. And this, you notice that this definition is a hell of a lot shorter than the other one. So it's like, well, what's going on? Equivalence, we had all this crap about the same number of variables and the structure is the same and blah, blah, blah. But this equisatisfiability is a lot simpler looking. It's just saying that one of them being satisfiable implies the other one's satisfiable. So what's up with that? When would something be? Why are we making a distinction here? Well, it's because equivalence and equisatisfiability aren't the same thing. You might not have the same number of variables inside of some Boolean formula that's equisatisfiable. You might be introducing new variables or removing variables to make it convenient for something like 3-SAT, which we're going to get to. There are reasons why slight variations of this problem become a lot easier to calculate, or just it may be faster for your particular algorithm or something. And so that is why we talk about this. So here's an example, something that is equisatisfiable. I'm not super thrilled with this one, but this is what it is. Introducing P isn't going to change the situation, except if P made it satisfiable. Anyways, that one's not great. A better example would be is if we had 2 copies of all of these, and each of so it's like literally all of these. Then we had 1 copy of it with a P and 1 copy with a not P. Then we're talking about, okay, well, we've introduced P. P wasn't in the original one at all, so it's not equivalent. But it is in fact equisatisfiable. So if there's some reason why you want to have 3, that may be a bad example because 2-SAT would actually be better. But if you had 3-SAT, then yeah. So equisatisfiability, as we're saying, there's reasons why that would be more helpful. So an example would be something like introduction of auxiliary variables because it makes it better fit a shape that we're looking for that's really easy to do satisfiability checks on. There's another one. If it turns out that there's some variable that has nothing to do with anything else, it's not going to change whether or not it's satisfiable. Well, we don't have to waste time looking at it all of the time. We can just throw it out. It's like, well, this isn't going to change anything about whether the rest of maybe some really complicated relation between a bunch of variables might change the situation. We just know this one variable, on, off. We don't care about it. We can just pull it out. And it's the same thing with, there are some circumstances, we're not going to cover that at all today, but where you can actually have a whole bunch of variables which are related to each other, but you've done basically a satisfiability check on just a subset. And so now we understand the behavior of those variables together. And so instead of trying to model them independently, we're just like, all right, you 5 variables, we're just going to treat like one new variable. Because the individual values of those variables isn't going to change the rest of it. In the same way as like, you might have an irrelevant variable, maybe it is the variables are only relevant in the fact that they could be true or false together, in a sense. And so, these kinds of techniques we're getting to equisatisfiable. So they're not equivalent, but they're close enough. Here is where the dragons live. Representing satisfiability. You say, what the hell could be a problem with that? Like, this seems like this should be easy. We're talking about ands and ors and nots, and we've already said things like we can convert from XORs and all this. We're just treating this like it's no big deal. Well, here's one of the forms that we might like to use. This was one that I used to play with when I was first learning logic, before I knew about CNF and DNF. I kept trying to reduce all of my logic, my formal logic problems to this. I didn't know this had a name, but I kept doing this. And I thought, oh, that's cool. Sometimes it seems to take a really damn long time to do that, but it's cool. I can do this for anything. And it's just the idea that you've got ors at the top level. Inside of there you've got ands, and inside of that you might have nots or just variables. Not variables or variables. That's it. So that is the entire thing. So if you can write a Boolean formula in this format, that is called DNF. That's just one of the formats that a Boolean formula might have. Another format is CNF, which is kind of the opposite. You've got ands at the top level. You've got ors inside of each of the conjuncts. So we call this a conjunction at the top level. Each of these is a disjunction. And then again, nots or just raw variables, either one. And so you don't have like 5 layers deep. It's only these 3 layers. That's it. That's it. You're never going to get like ors inside of ors or ands inside of ors inside of ands. Nothing like that. Just this. Just the ands at the top. And inside of those ands, you've got 1 layer of ors inside the parentheses, and then maybe nots inside there. That is it. Okay?
Sorry, I'm not seeing the difference. Can you point that out?
Yes. Notice the ors and ands. In the sense, we're flipping them. Now, to be clear, these mean very different things. So I'm just showing you what they look like. These 3 formulas mean very different things.
Okay, so it's all okay. So inside the parentheses, it's all ands in one, and all ors in the other. Now
exactly.
Okay.
Yeah, on the outside of the parentheses, it's all ands on one, and ors on the inside. And on the other one, it's all ors on the outside and ands on the inside, and that's it.
If you drew it as a schematic, you would have inverter and or inverter or and.
Yes. Yep.
3 layers. That's actually a fundamental gate in CMOS called and or inverter or and inverter.
Turn off.
I was about to say, did it get darker?
No. You got an idea, that was what it was. Okay, so now 3CNF is a particular variant of that. So we have DNF, where it's ors at the top level and ands underneath. Okay? So that is DNF. Ors at the top, ands underneath. CNF are ands at the top, ors underneath. Okay? So now we have a further variant ors underneath, but also every one of these ors has exactly 3 things in it. That's it. So like before, you know, we had like a 2, and we had a 3, we might have a 4 somewhere, we got a 1s.
Remember the 3 CMF just means up to 3, or it always means exactly
3 CNF means always exactly 3. And it is very important.
Oh, wait, does that include, constants? Could you use constants as one of the terms?
No, but we'll get to that in a second. 3 CNF just says that
Yeah,
there
that's
are 3. That's it. And they're all variables, so you don't have constants in here, you only have variables.
Yeah.
But 3 CNF says you will have exactly 3. Yeah.
You use the same variable twice?
No. Well, I don't. Some people might say yes. Some people definitely say no. I think.
If you say it's exactly 3, then for some reason it stinks.
Well,
Yeah.
yeah.
Depending on who you ask, there are differences there.
Because C and C or C are the same thing.
Yeah.
So
So you could put C twice and then it would be fine. But that would be one variant of 3 CNF. That would be okay. But if they want distinct ones. I left that out intentionally because different people will have different answers to that question. So you would need to go find out in that specific case, which one are we talking about? 2 CNF, very similar to 3 CNF, but it's all 2 variables each time. Okay?
22 CNF.
Did I do 22? Oh, I did 22. Yeah.
I was like, yeah, okay, what's special about 22?
Yeah. Well, it's surprising enough that 2 and 3 are as special as they turn out to be. We'll get to that in a second.
Sorry, can you go back to the 3 CNF again? Okay, so it's 3 inside, got it. Okay.
Yeah, so it's ands at the top. You might have a whole bunch of ands, in fact, you usually will.
Yeah.
But inside of each of those conjuncts, so the conjunction at the top, and inside of each conjunct, so that is each thing inside of parentheses, you're gonna have 3 things between ors. So that each disjunction has size 3.
I have a question about the 2 CNF slide. With the
Though it's not
bottom,
22 CNF.
with the bottom example, did you mean to start that?
Oh,
I did
or
not.
A, okay.
I did not.
Okay.
I did not mean that.
I was like, that.
Yeah.
He meant not
Something else.
J, I presume.
Yeah, I meant not J. I put all or, yeah.
This is the slide where you started drinking.
This was the slide where I stopped drinking as much coffee because it was time to go to sleep. So, here's the thing. All Boolean formulas, all of them, can be represented as DNF, and all Boolean formulas can be represented as CNF. But not all Boolean formulas can be represented as 3 CNF. And not all Boolean formulas can be represented as 2 CNF. Okay? But all Boolean formulas do have equisatisfiable Boolean formulas in 3 CNF and 2 CNF. And so that's where you're gonna like introduce like fake variables you don't actually care about that gets you into 3 CNF or 2 CNF. However, okay, notice I said have. They do have. They have. I didn't say that you want them. I said they have them. It's a thing. It exists. Okay? Because conversion between these formats is not free at all. Sometimes it is cheap. Sometimes it's very, very much not. So you can't assume, even though these things are all well defined, and you can probably even intuit in your head how you might switch from DNF to CNF. You would probably be right. If you made the algorithm for it, your guess would probably be right. And then you would go give it a mildly interesting CNF, and you'd be like, why the hell did my computer run out of memory? And then you're like, well, let me go buy the biggest computer they have at Amazon and try it there. And you're like, wow, that ran out of memory very quickly too. It's like, was there a memory leak? No, there was not. It's just gonna happen. It's gonna break the crap out of whatever you're doing, sometimes, depending which direction you're dealing with. These things don't always play nice. So let's put a pin in that for the we're just trying to figure out if you give me a Boolean formula of some kind, is that thing satisfiable? That's it. That's all you're trying to figure out. You don't care sometimes you want to know about how many times it can be satisfiable. So they call that like pound satisfiable or count satisfiable or whatever. Sometimes you care about if it's falsifiable. That's another interesting one. So you can get to falsifiability. That's an interesting one. We can cover that in a minute. Sometimes you want a specific example of one that does, like an assignment that does satisfy it. And so we would call an assignment that gives you a particular property a witness. I mentioned that briefly earlier. So if you've got like an assignment that gives you satisfiability, that would be a witness for satisfiability. If you had an assignment that gives you falsifiability, you get a witness for that. Can you have one witness that gives you contingent, which is both satisfiable and falsifiable? Anybody want to take a yes? No. You couldn't have one witness, one assignment that gives you both true and false. So in a sense, a witness, if you wanted to construct the equivalent notion of a witness for contingent, that's two different assignments. Then you could.
So is a witness and an assignment?
Yes, a witness is a particular assignment.
Okay.
A witness is one of the assignments that's enough to show you something is true. Or false, or pardon the pun. A witness is a particular assignment that says that this witness shows that this one is that it's satisfiable, or this witness shows this thing is falsifiable. An example of this would be like if you gave me an integer, and it's a really big integer, and you're like, factor this giant integer. It's like, oh, that's going to take me a while. On the other hand, if I said, here is one of the factors of this integer, you could check that really quickly. That would not take you very long at all to check if the integer I gave you is a factor of another one. Which isn't to say it's the only one, but it is a factor. You'd be able to quickly find out if I gave you a factor. So there are several different variants of SAT. Okay, if you're specific, so SAT was very generalized, just saying find out if this Boolean formula is satisfiable. Didn't say anything else about the Boolean formula. We just said is it satisfiable. Now we're talking about specific ones. DNF SAT. If your Boolean formula is in DNF, tell me if that DNF Boolean formula is satisfiable. That is a particular problem. There are algorithms you would use for finding that answer. There's CNF SAT. My Boolean formula is written in CNF format. Tell me if that thing is satisfiable. There are special algorithms for that. 3SAT. My Boolean formula is in 3CNF specifically. Now tell me if that's satisfiable. Same thing with 2SAT. Okay? And as we said, all Boolean formulas can be written in DNF and CNF for sure. And so we know for sure that those two, in some sense, are possible things you could do on any Boolean formula, eventually. But what do we mean by eventually here? So, I don't know, we're definitely running a little tight on time, but complexity classes, I think for the moment I'm going to assume that folks are familiar with that complexity classes are a thing. We're all cool on that? Okay. We're going to skip past that then. Decision problems, just suffice to say, if someone's saying a decision problem, that is a particular way of framing a complexity problem. You can turn some other kind of complex problem into a really specific structure of a problem that we can do some kind of analysis on. Again, it's not something that you're going to need to deal with a whole lot, other than if you see people talking about decision problems inside of like a paper that you're reading about this stuff. It just means there's a special way that we have reformulated the question that makes it really nice for doing a particular kind of analysis on it. So it's not, all the things that we're talking about, the problems that we're talking about, have decision problem versions of them. So it's okay. So now, one of the complexity classes is called P, or equivalently P time. It is a problem that can be solved by a deterministic Turing machine in polynomial time. And a time that is polynomial to some aspect of the input. Maybe it's the length of the input, maybe it's a particular integer value of the input. If you gave it like a number to factor, then that, you know, or to perform, maybe not factor is not a good example. If you gave it some number and you wanted to perform some kind of calculation on it, then n could be related to what calculation you need to do.
You want to divide the number, the length of the division is dependent upon the size of the number.
Yes, that would be a good example, yeah, yeah. So it's worth pointing out, DNF-SAT is in P, which might be a little bit surprising to folks who have a little bit of familiarity with SAT solvers. It's like, what? No, DNF-SAT, for real, is in P. It's super easy to do it, and frankly, it might actually be in another class called L, linear time.
Oh, so yeah, where you only have to make one of them true.
Yeah.
And then that, it's and short circuit.
Exactly. So it turns out, yeah.
Is DNF fall, or is there a falsifiability version of the SAT problem?
We'll get to that in a
Is
second.
that equivalent to CNF SAT?
We'll get to that in a second. So DNF-SAT is, all you have to do is find something which satisfies the DNF. But because the DNF is disjunction at the top, a bunch of ors at the top, means you, in order to get satisfiability on one of those, it's a Boolean formula, but in order to get satisfiability, the only thing you have to do is find one of them that doesn't already contain a contradiction. Like, if it already had contained a contradiction, move on to the next one. The only way a DNF would be unsatisfiable would be is if literally every single one of them is already a contradiction. And so one of the ways that you would know that a DNF, you know, doesn't have any contradictions is if none of the thing that we were saying earlier, can the same variable be in there twice? With DNF, if you've constructed your DNF in a way where each of those conjunctions inside the DNF, you know, or disjunction at the top, ors at the top, ands underneath, if each of your sets of ands, the variables only show up one time, there are no contradictions. There couldn't be, because they're all one at a time. So if you found one, it's instantly satisfiable. So if you have a DNF, and each variable only shows up once inside of your DNF, inside of each conjunct of your DNF, or at most once, instantly you know it's satisfied. So that's cool. Like, so then we're talking constant time. But even in the worst case where, yeah, well, you know, the same variable shows up 10 times, you know, it's like this and this and this and this. It's like the same variable may show up like a bunch. Well, then it just becomes either linear or possibly log n. It's definitely not getting above n. It might be, it's not getting to n squared. It's just like n. So it's not even polynomial, it's like linear. So another interesting one, 2SAT is also in P. So remember, 2SAT was CNF. So at least we could have dismissed the DNF thing. It's like, well, that's because of DNF, and we've already established that maybe getting DNF somehow explodes in some very not good way if you're starting with something that's not already known to be good for DNF. But that's 2SAT's a CNF, and it's in P also. So now we're going to talk about a different category, NP. So NP is also solvable in polynomial time by a magical, non-deterministic Turing machine. and in fairness, we have, to a certain level of magic, we have magical non-deterministic Turing machines now. They're called quantum computers. So it turns out that it's not entirely the same thing, but that is one way you can kind of contort the problem a little bit. The complexity class for things that are solvable with quantum computers is a little bit different from NP. But there is a relation. So somehow magical, non-deterministic Turing machine that we are leaving unspecified is able to solve the problem in polynomial time. And it turns out that things which can be solved in polynomial time by a magical, non-deterministic Turing machine turn out to be the exact same problems that can be checked by a deterministic Turing machine in polynomial time. That's an interesting computer science thing you can dig into if you're curious. But here is according to the Cook-Levin theorem, CNF set, so not DNF set, CNF set, where we're starting with the ands on the top, ors underneath. Okay? That is NP complete. In fact, that is the definition of NP complete. It was the first thing that we showed had this property. Anything that would be inside of this, computable and polynomial times of these magical non-deterministic Turing machines can be solved by something which can solve CNF SAT. That's the magic sauce that is NP complete. And so CNF SAT was the first problem shown to have this property. That anything inside of NP instantly turns into, you can turn it into instantly. There may be a translation thing, but you can solve it with a CNF SAT solver. So 3-SAT, one of the really important things that they also proved is NP complete is 3-SAT. And so that is an interesting property that instead of just the generalized CNF, it's just specifically the CNF using just the 3 variables version, which again we said, if you introduce these fake variables inside of there, then you can buffer them out to 3 if you have fewer than 3. And in fact, a lot of CNF SAT solvers, which we would just call SAT solvers, because DNF SAT is really easy. If we're talking about a SAT solver, we're talking about a CNF SAT solver. A lot of them turn it into a 3-SAT. And speaking of, converting from CNF to 3-CNF, that can be done in polynomial time. And that's the trick. Any CNF can be turned into 3-CNF in polynomial time. That was an important discovery. Weirdly, it's one of those computer science discoveries that doesn't really have a name associated with it. There's like, what's the name of this algorithm? Man, I kept looking and I'm like, okay, I don't know the name of the algorithm. Someone knows the name of this algorithm. Now tell me the name of this algorithm. And I keep digging and I keep digging, and no, there is no name for this stupid algorithm. Which is shocking. There's no name for it, but there's no name for this algorithm. It just exists. So, but it's basically you're just going to turn an arbitrary CNF into 3-CNF so that you can put it into a 3-SAT solver. And this can be done in polynomial time and space. It'll make the formula, maybe it might square the length of it, but it's not going to be like truth the end length of it, which is what you would get if you tried to go to DNF. and that's one of the things that's kind of weird to think about, because we said DNF SAT is like, man, we're not just talking about polynomial time, we're talking about things linear. Like, so that's the solution. We know we can turn a CNF into DNF. Every CNF can be turned into a DNF, we know for sure. Let's just do that. Well, turns out, doing that is so hard that it's actually, if you were doing that to try to get to SAT, like maybe there's some other reason you're doing that, but if you're doing that to try to get to a shortcut to SAT, it's actually faster to solve CNF SAT than to convert from CNF to DNF and then use DNF SAT. Even if we pretend like the DNF SAT is free, literally free, 0 time, it's still faster to do CNF SAT than to do the conversion. And so that's one of those weird, you wouldn't expect, but that is the situation you're dealing with here. Like it is the size of these DNFs that you convert to. It turns out that there's actually a result where it's not just, one of the ways you can think about it from complexity theories, it's not just n squared or n to the k or whatever. It's actually like 2 to the n, where the interesting thing is it turns out converting CNF to DNF is known to be bounded from below by 2 to the n. It's actually, you can't even get to it. You can't get to it to the n. There is no algorithm that will get you that conversion in 2 to the n steps. It's slower than that. But you could get close to 2 to the n steps from above. It's rough. So probably not what you want. And it turns out it's the same situation with CNF to 2CNF. And so that's one of the interesting ways that some people model P versus NP, is we we actually weren't super confident that there couldn't ever exist a way to get from 3-SAT to 2-SAT, to get from 3CNF to 2CNF. Maybe there is some trick and no one has just found it yet. But turns out that is one of the ways that people are looking for p-persistent. So falsifiability solver, just a real quick before, because we got to hurry up and get to the silences part as well. So on the falsifiability side, you know, we were talking about satisfiability. Your compiler wants to check this guard. Hey, do I need to include this chunk? Because, okay, now I know it's satisfiable, so that means I have to have the code in there. Falsifiable. Well, when you negate a CNF, so if you think about that, this is De Morgan's law, you're going to get a DNF. And we already know DNF's bad, except, wait, is it bad? Like, it feels like it would be bad. We know, go from CNF to DNF, bad. We've already established this. We're all on the same page. Except, if you're negating it,
You need to do the other side too.
all you're doing is flipping all the variables. And flipping the ors to ands. That's it. And so now you're talking about, you have your problem already in this structure, which is really optimized for CNF. You've just changed the meaning of it. You just changed the ors to ands, and you just put, you know, whether there's knots in front of everything. Now you feed the same thing to a DNF solver. Boom, you got it in no time. Which is why it's shocking to me that I can't find an example of even one SAT solver that ships with a copy of DNF SAT. Like, I can't find one. Maybe there is one. It seems like an obvious oversight. Now, granted, you're not going to get extra points at the SAT solver competition for also having a DNF SAT. It's really great. They're like, no one cares. 0 people care. But also, from the perspective of like a working programmer,
Falsifiability.
well, yeah, that matters too. And so,
The code I wrote for that BDD article, you can use BDDs to do SAT solving. It's not the best way, but it's sometimes efficient, okay?
yeah.
And so it's just very easy to, in that satisfiability procedure, the thing you're trying to find an assignment that evaluates to true or an assignment that evaluates false. Well, that's just a parameter there. And so if you code it that way, you do that both for free.
Okay, yeah. And so, yeah, I mean, so there are definitely tricks that we can take. I mean, as far as the high-level algorithm is concerned, that's the thing is like.
But what I'm saying is equally efficient in this representation thing.
Yeah.
Doing that.
Yeah. And so that's the thing here is like, in general, if you did the hard work to get something ready for a SAT solver by putting it into CNF, getting falsifiability is way easier from an algorithm perspective. But it's not usually a first-class thing that they talk about inside the system.
Okay, just the point I'm making is that the BDD representation, depending on the ordering of variables, it can be a very efficient way of solving these problems. And so, anyway, that's sort of like the heuristics that the SAT solvers use. Depending on the heuristics, the SAT solver may be efficient or not.
Yeah.
So all I'm saying here is that there's at least one way to write a SAT solver with the shipping solver that you can just get, like you're saying, one exists.
Okay.
In which you do have that option, and not just a fake option that's going to take forever if you do it this way.
Yeah. Okay, cool. I appreciate it. Well, if we can get you on the Zulip and post like the details or whatever. Yeah, thank you. So yeah, as a result, it turns out a DNF SAT solver turns into a falsifiability checker with just a little bit of work. So I definitely run out of time on this one. So, but DPLL is kind of the high-level approach that you would take that involves backtracking and variables. CDCL is a subvariant of DPLL. It is a more popular, more common one that we use today, constraint-driven clause learning. And so that is, these are kind of the main approaches that they usually take today. It's worth pointing out that there are other approaches to stat solving as we are talking about here. They're completely separate from these. And it turns out that we don't have a generalized way of knowing which stat solver is going to work really well on your stat problem, if any of them will. Because in general, stat problems are still in peak, and so we don't have a really good, reliable way of knowing which stat solver to use in your circumstance. We don't know if it's going to be one of these, it's just not going to behave well at all. But on the bright side, as we're going to see, we have reason to think that some of these we have good answers for. So. Sorry, Scott. Yeah. You need the. Yes, that was the here's the stage right here. Okay. Oh wait, I think I have two going on, so it might seem. Oh, how do you turn off anyway? On Chrome or? Oh, it's the first year of Windows. Yeah. I didn't say. Right. Sorry. Flux.
Claims is off.
Flux is off.
No, claims is off.
I don't know. It says.
It says turn on now, so it's schedule night turn. You can turn schedule off.
Flux is on.
Yeah, your flux is on.
Okay. Yeah.
There we go.
Hey.
All right, solve one satisfiability problem. Okay, not fun. All right.
Slideshow.
Here we go. All right.
Browse through all the
Anyway,
tabs.
so to take it over from Charlie there. Yeah, I was going to go more in depth on using stat solvers to solve practical problems. I posted a link to the code I uploaded, which applies it to specific problems. You can see that in the either comment section or on the Zulip app if you want to do that. Use the usual. Sorry, still use Python. I'm kidding. It's not the ideal one for the hyper rigorous languages like Haskell or Boolean. Anyway, usual virtual environment. You can install requirements from pip. Charlie covered a lot of this stuff in this side. So what SAT is, how it's NP-complete. It's equivalent to a large class of constraint problems. So if you have a constraint problem, you can convert it back to 3 conjunctive normal form, then one of the existing stat solvers can take it and run from there. Just as long as you can do the conversion between what your problem is and the version that the solver likes to look at. Great way to think of it is like a breakdown in responsibilities. There's going to be like something that's really good at solving 3 conjunctive normal form. In this case, I've worked with a C3 library, or an interface to the Microsoft's C3 stat solver. So they basically just have to be very good at solving 3 conjunctive normal form Boolean problems. Then there's like an API to Z3. So basically what you have to do is feed it constraints in a way that it understands, and then that library converts it over to Z3's preferred form, like the 3 conjunctive normal form version of the problem. And then, as I like to say, that means you no longer have to be clever about how to optimize a variable. Like the C3 engine is very good at solving it, and so basically converts it so that your problem is just your job is just a matter of how do I specify my constraints in a way that the Z3 API understands, so that it converts it into the 3 conjunctive normal form, and then you can solve it from there. Won't go too much into depth in this, but just give you intuition on what's going on about how this kind of thing can happen. Like for example, in general, one constraint you might want to add is one integer variable is greater than another. How does that turn into Boolean variables? Well, you'd have the Boolean representation of it, and then you basically convert it into, well, if the high bit is 1 on the first one, and the high bit is 0 on the second one, that means the first one is greater than the second. Basically, doing a bitwise binary comparison is how you would know one integer is greater than another, and so ultimately that's how it converts down into Boolean variables.
Unfortunately, you don't have to know all those details. If you're using an interface to a SAT solver, all you have to do is add this constraint here. You declare A and B to be integers. You've added the constraint that A is greater than B, and then it deals with all the details of how that turns into Boolean variables and something that can be fed into a SAT solver. What would be another one? Distinct, which would be one that comes up a lot. I have 3 variables. They all must be different. Same kind of concept. I won't go into a lot of detail, but conceptually you can break it down into Boolean variables and have a large expression. Instead of dealing with all those details, you just have to use the magic distinct command. It takes care of that for you. A lot of them have utilities for doing not just satisfaction, but optimizing, finding the largest value subject to these constraints. That would be the code for it. So, to get to a more concrete problem. Let's say you want to use a SAT solver to solve Sudoku. Everyone knows Sudoku? Okay. All right. What's one constraint that Sudoku problem has to satisfy?
1 through 9 in each column and
Correct.
row and
You got a 9 by 9 grid. All of them are integers. What's another constraint?
oh, right to that level. Okay, yeah, that each of them is an integer 1 through 9. But yeah, you have in each row there's one of each. Each column there's one of each. And each square.
Or as I would put it, like in each row there's a distinct integer, the 1 to 9. Each column there's a distinct 1 to 9. Each box there's a distinct 1 to 9. Those would be the constraints that apply to all Sudoku problems. If you wanted to solve a specific Sudoku problem, you say, it's all those constraints, and then say, this cell has to be 6, this cell has to be 5, and then that narrows down to the specific problem you're working on. Make that a little more concrete. Let's go into my horribly unoptimized coding environment. Just run through what it concretely looks like. So there's, for example, code I have. Make it more concrete what it would look like. What are we doing? First, you initialize the solver. Here, you've defined a grid, 9 by 9 grid of variables. You have to give them names and kind of name the variables based on their position in the grid. Here, I add a constraint that, of course, everything in it is an integer, greater than 0, less than 10, so it puts it at the 1 to 9 range. Here, I added the distinct constraint. Basically, for every row in it, I iterate over the elements of that 2 by 2 array and say that it has to have a distinct value across that subarray. Same thing for columns. A little bit tricky to have it specify that for a box, but you can fundamentally what's going on is enumerating everything in any particular box that can exist the same. The values have to be distinct across that box. And then just to do cute little ASCII art. Oh yeah, I just made it so that you can give an ASCII art of a Sudoku puzzle and then it correctly parses it and plug in a specific one here. I don't know how to choose purple for it, but fundamentally you put in, just made it so that you leave question marks for the unknowns and then you specify the known values, and then at that point you just read it in, add those as constraints. Here's a specific line where you add the constraint that's kind of read in from that's added in from the input, and then that's it. You just a lot of commented out code, and then final code at the end where you solve it. You just want to see the final payoff. Yeah, just spits out the solution. Oh, actually, maybe I had a time. Okay.
I got a bunch of questions.
Oh yeah, please go.
So you can set up Sudoku problems that have multiple solutions. What does your program do about, problem states that have multiple solutions?
The way it's written, when you ask it for a solution, the code has given, see if I can pull it back up. As written, all it does is it gives you some solution that satisfies it. There's a different command. It's not guaranteed to give me a specific one. There are different commands that I'm not using right here that'll say, give me every solution. And assuming for a second it doesn't give you give me, one kind of workaround would be, once you get your solution back and you're like, well, I want to know the second solution, you can kind of work around it yourself by basically saying, okay, I have my original constraints, I'm gonna add one more constraint, which is that it can't be the solution you just gave me. And then that will allow you to pump out more solutions. Sorry, let me give Misha a chance and if you got more.
The inverse of that of no solution, but.
Yeah,
in that case,
there's a
there's a
solution. How long does that take?
I actually don't know that in practice. All I know is that I have a catch. This isn't the correct way to catch it, but in cases where it is, it generally comes up. In my practice, for the problems I've worked on pretty quickly.
Wait, so what happens when you uncomment that this line makes it fail?
What?
The comment that says this line makes it fail? With a solver.add 9 equals.
Yeah, above your solve.check.
Where your cursor is right now.
Oh.
So if you add that line back and rerun the code, what happens? Does it actually break it? And like how long does it take for it to say no solution?
Sorry, I'm not gonna.
Move your cursor up 5 lines.
Okay.
Yeah.
This.
See there,
Two more.
Oh, gotcha.
See the line says makes it fail.
Okay, okay.
Add that, you add that,
Yeah.
And then rerun it.
Yeah, well, since it's
Or is that like a hard-coded one before you have the ASCII art?
sorry, what?
Just right, yeah. Unset.
That's right, it just triggers the branch. Yeah, it's pretty.
So
Remember, by the scale of like things computers do, solving Sudoku is pretty quick, so you can expect that it'll find it's not satisfied.
okay.
This is only doing satisfiability, so how do you know if something even has, I mean, obviously you can say, okay, let me block this solution out, so now that one's unsatisfiable, but how do you know when you run, I mean,
How do you know that it's genuinely unsatisfiable?
how do you know the number of satisfiability solutions?
Oh,
I think
yeah.
that's beyond the.
That's a different, it's a different problem.
Class of problem.
That's a different class of problem?
Yeah, the Z3 should be able to get you.
Well, that relates to the earlier question, like there are versions of it where it just says keep going until you find every solution.
Okay.
And it's basically that thing, like, once you get a solution, add a constraint that can't be the solution.
Okay,
And
so it doesn't know that it's found the final one, but it just keeps adding a constraint, finding a new solution until either it runs out of time or it returns it unsatisfied.
So it can, it's a slightly different approach that it will take.
Okay.
Doing it. It starts the same way, but then it goes in different. So
Okay.
I will point out that, what we're doing here is an SMT solver. So it's one layer on top of the stat solver. And
Okay.
What's happening, all of our like integer statements, there are notions that Z3 is really good about knowing, how to turn really common things we want to ask about into things that look like Boolean variables are shoved into a stat problem.
Okay.
And it is mostly a stat solver, but there's a little bit of like a layer on top of it.
Okay.
And so that's why we're able to talk about things like integers inside of a stat solver. It's like, well, it's just like a thin layer it's putting on top. It's not, most of the work is in stat. But a lot of the things that you might want from a stat solver, like give me the number of solutions that exist. There is a version of the SAT problem that is that.
Okay.
And a lot of our SAT solvers, including the one that Z3 provides, will be able to give you answers to that. But it's just, you have to ask a slightly different question.
Okay, that's fine.
Okay, one more question.
Sure.
Can you talk about the complexity of your solver, as it relates to size? Like, if instead of saying 9, you could take any number and cube it, so really this is like a 3
Like a
square
hexagon.
solution.
Right, actually, I can't authoritatively on that. All I know is that like whatever it's working on is probably one of the faster ways you can find the solution. I don't know exactly about the scale. I know in practice it finds a lot of shortcuts and redundancies.
To open up behind the scenes a little bit, the Z3 that he's doing is not happening in Python.
Oh,
It's generally written in very optimized code, generally C or.
Yeah, it's Z3 to C. Yeah. So it's just the Python wrapper. But there's also like directly for SAT solvers, there is so there's picosat, which is one of the SAT solvers we were talking about earlier. There's picosat, which is just a Python wrapper around picosat. But Silas is absolutely right. Like if you're gonna do something interesting, you're probably better
guess, for,
August.
what does that mean? Sorry, what was that?
Satisfiability module of theorems, but yeah.
It's at 8:30, so technically out of time. But
Okay, yeah, well, we keep going for a few more.
this is just applying it to like more problems. Like one of them came out. This might be like overkill to use SAT-solver for this because it's a relatively simple problem, but found a problem in like a reverse engineering challenge where it's like, okay, you can inject shell code that's limited to certain bytes, and I had a case where I wanted to add a specific value to the stack pointer, and the problem is the values that you add must themselves be from the constraint set, so you can't just add an arbitrary value, you can only add values made up of specific bytes. So I had a problem of find a way to add the number I really want by breaking it into numbers that only use the valid bytes. You may follow so far. It'd be something like find numbers that add up to 54, but you can't use 5 or 4. So that'd be a much easier version, but that's the idea. The other one, my latest obsession, this game in one called Dungeons and Diagrams, it's a constraint problem. In fact, I have it still pulled up. I mean, you really could call it on time, this was more of my interest.
Go for it.
Oh, good to know, so to make this easier. Okay, there's this neat game on, sub-game on Last Call BBS from Zachtronics, where what it gives you is this grid that you're building a dungeon. It tells you how many wall tiles have to be in each column and how many have to be in each row, and has other constraints like monsters have to be at the back of dead ends. You cannot otherwise have any dead ends. And a treasure chest must be in a 3x3 room with exactly one entrance. And I know, vomited a lot of stuff at you, but fundamentally, those are all constraints. I've been building up a SAT solver to solve problems like these. To make it a little more concrete, if I were solving this, the first thing you notice is this does not have any wall tiles, and I would mark that as being empty. We know monsters have to be at the back of the dead end, so if you know the open tile that reaches a monster, you know it otherwise has to be surrounded by walls. There's the wall tile. This monster is facing an open point, so this monster has to be at the back of the dead end, so you kind of fill that in. What else can you do?
What was the treasure chest one?
It has to be in a 3x3 room, that is, 3x3 blanks, and has to be surrounded by walls with exactly one entrance to the room. So I'm gonna kind of, you notice that this looks like a dead end, you can't have a dead end, so that has to be filled in.
All 3x3 rooms will be constrained.
Yes, the only way we could make this would be fill that in, and that satisfies the 4. Let me take this aside. This is a lot to explain. You just want to come and look at these.
That's really cool. Yeah. Can you post that to the Zoom?
Post the Dungeons and Diagrams.
The game.
Sure. Well, there's this is all within like a Steam game, but there's a there's a website within like open source reimplementation tool, and that has 1,000 problems on it, all of which I've solved.
Oh, dang.
So yeah, I'll post that.
Yeah.
But yeah.
Cool.
Thank you for listening.
Cool. I'm really interested in the game that you built.
Are you gonna
as
show
well.
our SAT solver offline tomorrow?
Let's,
Find something interesting.
go sample that.
Perfect.
Yeah, okay, all right, I can show you.
It's quite a bit more interesting than Sudoku. Because Sudoku, you just recursive, like in one word.
There's more stickers over here if anybody wants some of the formal methods user group stickers.
What's explain the design?
So,
Armadillo PBD. What else is there?
So, yeah, there's so many left. Yeah. So,
I built like
I was trying to figure out what logo to put on the Meetup, because it's better to have a logo than to not have a logo. And so I was trying to figure it out, and then I was like, well, there's lots of text-based logos I could use. But text-based logos don't work as well as some graphic ones. And so then I'm like, well, it should be something at least moderately absurd.
that's.
So I was like, ah, I got it.
Yeah.
I was like, that, I think it's
So this is add the constraint,
Right.
the whole dictionary is.
Well, like,
I just
so
made
I
my
have
idea
a
speak
word
for
thing
myself.
that I
So
generate,
I took
and then there's
the
also
public
constraints
public
amongst the
domain
words themselves.
and I just
But I wrote
did
my
an offset and then like
not
looked up the
so now I'm
RFC
like,
for RFC, you know, like,
with the
ah,
set solver.
start
But
here.
similar to
And then
the
do
that you
here.
have, which is why I asked
Say
it,
that I
like,
want it to be
I
completely filled with black,
specifically want
okay.
and that's the
We
biggest
got
problem
plenty of them,
with
so
most
if you need
people
plenty,
that say
we
like,
got-
I want to write a thing, I'm like, yeah,
That's
your
awesome.
puzzle has
Cool.
like
And that's
10
on your site?
like 2 or more solutions.
That's on your
But yeah, so, we,
Before you go,
Yeah,
you're
I
talking
think,
to me.
I'm going to give them
Common target goal.
so next month we, will be before the
So I think it would
ACL2
be
conference,
cool if you
so
made
we could
your
have a talk on
sequence over,
ACL2 if
have
there's
that
interest.
size variable. And
Otherwise we
so,
could, we could just go
we
and see if we get one of the
had
speakers from the
a
ACL2
5
conference
size
in May, come and like drag them back out and review that talk again. I'm also
Is that how you
totally full of this plan.
Yeah, that's totally my plan.
For,
What would be the private
June,
version or the?
it is,
Well, instead of 3 squared to make 9,
it's
it's 1
after
squared.
the NASA formal
So it's
methods.
25
So NASA formal
25
methods is
boxes.
in the beginning
With
of
the boxes
June.
of 25.
So ACL2
Yeah.
conference
Five by
is
five by five
the
by five.
second week of May,
Right.
Monday and Tuesday.
And so,
Up here at
The main problem
campus.
is just getting,
well, that's.
Tickets are open, I'll post inside of the, oh, I think I already have, I posted it on the Zulip, so if anybody wants on the Zulip, you can get signed up real quick.
I had another version of that where there's other reverse engineering.
Yes,
problem
we
solving
need to
and
do that,
you have to figure out
the ACL2 conference, the sign up is open now, so if you wanna go, that's that Monday and Tuesday of like, second Monday and
after
Tuesday
going
of
through that function.
May.
Okay.
NAS formal methods, sign up isn't up yet, which I'm surprised by, since it's in June, and they have a lot larger leeway than most people do, but, that's gonna be in Williamsburg, Virginia, and then the next one in the US after that is, the hardware one, FMCAT is gonna be, in, I think Silicon Valley or something in like October or something, so.
So how do we get signed up for Zulip?
Zulip, okay, give me emails.
I thought it was really easy.
Huh?
Did it sign me up? No,
No,
I
you
sent,
used-
I sent you a link.
Yeah, you sent me a link and I said that was really easy.
Yeah.
Oh, no, if you use the QR code and you ask it to create an account, it says this is only invite only.
Yeah,
So-
I didn't think that.
Then I guess if Charlie sends you a link, it's really easy.
Okay.
Charlie, I'm gonna kick off, I gotta.
Yeah,
If you're on Zulip or.
Yeah, we'll see you then first. Yeah. Alright, emails.
I have an open source GitHub repository for it. GitHub.com/turnup-the-mic, TURN. Just like that, and it's me and my puzzle is a camouflage puzzle.
Okay.
This
Anybody
is
else
also
want?
in Python, so.
Here's mine for Buzzbang and all caps
If
on
you wanna see
But,
creative puzzles, I have a play
MEG.
creative puzzles and you can see it.
B-U-Z-Z.
No, B-U-Z, M-E-G.
Okay. At,
All caps
all
are-
caps.
PDF, so.
One four,
G-U-P-T-A. Maybe my name is broken.
Right?
It's all right. DPL block folder, and then puzzle to play, and so these are PDFs of the puzzle that it's generates.
Cool.
And then
Good job.
Yeah, thanks for coming out.
rules to it,
It's
and
a lot of fun. I think it's so cool to have a meetup that's not like related to entrepreneurship or blockchain.
I know, right? Although we have threatened at least once, so like, if the numbers of people who show up ever gets too low.
Yeah,
We're
we
gonna
reserve the
feel
right to pull the
obligated to
emergency
say-
brake.
To pull the emergency brake, which is to say out loud in the right coffee shop.
Oh, gotcha.
Hey, did you hear that the formal methods group is gonna be talking about blockchain next week? Cause that was so up for, like, But that is our last resort. So that is.
Break in case of break glass in case of emergency.
Make sure to tell your friends so that we're not stuck doing that.
I have to be, you said it was five
which, you want to do?
I'm on the Zoom.
Oh, yeah.
Yeah, make
every
sure
five
to-
graders were.
I'm like, really? You're a quarter?
Well, no, it was not true.
And then.
We know better than
Across
that.
this, the words and stuff.
Okay, cool. I will send it.
It has a different word in each.
Yes, that is true.
Yeah.
Well, I mean,
Charlie, you need help dating anything else?
Yeah.
I guess I don't technically have that as a constraint, but.
I think we're doing okay. We
But I've
scheduled all
actually
the,
never seen a.
chairs in, and yeah, I'll leave
Oh,
that.
you said the same word, but the answer key is a different letter.
Oh, thank you.
But in that mess is a puzzle validator, so if I try to generate a puzzle, then I do get to a section where I'm like, try to give me how many solutions are there, and if you try to create a puzzle that has more than one solution, it's like, you have.
Yeah,